How's everybody doing? Welcome back for Math for Healthcare video lecture series. And today we're going to start looking at conditional probabilities. But first, we'll take a look at this table of a survey where a medical researcher surveyed a large group of men and women about whether they take medicine as prescribed. The responses were categorized as never, sometimes, or always, and are shown in the following table. Let's say we want to find the probability that a randomly selected person takes their medicine sometimes. Well, let's see, the size of our sample space is the 10,000. 10,000. And how many of them sometimes? And this is just same person, not men or women, so there's 3,400. Okay. So that's equal to 0.34 or 34%. And how about if we want to find the probability that a randomly selected person takes their medicine sometimes or always? Well, let's suppose we say that S is the set of people sometimes, and A is the set of people that takes it always. I'm not going to write it down because I think that it makes sense for us. And so here we're looking for the probability of sometimes or always. And here we could really just do the probability of sometimes plus the probability of always. Why? Because sometimes and always are mutually exclusive events. You can't be in both of those. Okay? And so the intersection is empty. And this is going to be 3,400 over 10,000 plus always is 5,400 over 10,000. Okay, and that's going to be 0.88. Okay, good. Now, find the probability that a randomly selected person is a female and never takes her medicine. Okay, so I know it says when, but let's say we let female be F, the set F, or the event F, and we're looking for, notice the word and never takes her medicine. So we're looking probability of female and or intersect never. And this is going to be, while there, in a chart, this is the intersect, no, my bad. We have the intersection is never right there. So this is equal to 636, right? Female and never over 10,000, which is 0.636, right? Okay, so that's intersection. We have and. Now, we've got to be tricky here. Now, the next question, if a randomly chosen person takes their medicine never, what is the probability they are male? So try and think about that reading this chart. What it's saying is we know the person takes their medicine never. That means we're talking about a total of 1,200 people. We know that it's one of those people that took it never. And then we want the probability that they're male. Well, how many of those 1,200 were male? Is 564. Okay, so what? That's a little less than 50% or something like that. Probably 0.48. I'm not going to calculate it. It's approximate, right? 600 would be 0.5 exactly. Okay, I'll do it. 564 divided by 1,200. 0.47. Oh, geez, that's really close. All right, good. Now, the tricky thing is distinguishing between this third one, female and never, where that's intersection. We're looking for the probability of an intersection, and it's and, okay? And then over here, what we had down here, let me go in red, number 4, that's a new thing. And notice the sample size changed, right? Or sample space changed. So here, this is going to be a new type of probability we call conditional. And I want you to all, while you're watching these and doing these, is the tricky thing is to distinguish between intersection and conditional. That's going to be for the rest of this chapter. That's always something you got to pay attention to, because it's a little tricky. They're related, right? Both things are happening, but in one of them, we know something's happening. And in general, the probability of an event is affected by the occurrence of other events, or knowledge that other events will occur. These occurrences and knowledges are conditions that modify the underlying sample space of the original problem, which is why we change the sample space. So let's look at another example. 2 cards are drawn without replacement from one well-shuffled deck of 52 playing cards. What is the probability that the first card drawn is a king? Okay. Well, king, first card, we got 52 cards. There's how many kings? 4. So 4 out of 52. B. What's the probability the second card drawn is a king, given that the first card drawn was not a king? Well, let's think about it. Similarly to the last one, well, there's 51 cards left. I know that the first card was not a king, so that means I still have 4 kings left. Okay, so it's 4 out of 51, or 4 over 51 is the probability. C, what is the probability that the second card drawn is a king, given that the first card drawn is a king? Now notice here, my sample space, I only have 51 cards left after big thing here is without replacement. I only have 51 cards now. Oh, but I know that the first card was a king, so that now there's only 3 left. So when determining the probability of an event, if we were given knowledge relevant to whether another event occurs, it could change the probability of our event. And this is called conditional probability, since the probability of an event occurring that another event has already occurred. We can use a Venn diagram to investigate this further. And let's think about how. Okay, let's say here's my Venn diagram, right? And I got events A and events B. He's A, he's B. So what happens here is, let's say we know that A occurs, right? What does that mean? If we know A occurs, we know we must be living, or whatever, must be inside this green area, right? We know A happens. So that's the new sample space. And then how is it possible for B to happen? If we know we're already in that green area, you remember, it's kind of like that green area is now the new sample space, because we know that's what happened. And the only way B could happen there is in this yellow area, or the intersection of A and B. Okay? And so that tells us when we have a conditional probability, our formula should look something like the probability of A intersect. Well, let me write it. Let's start again there. And I won't blow. So now we want the probability, we know A occurs. Probability that B occurs given that A. Well, what we saw was the new sample space is A. So that's our new denominator, the probability of A. And then the numerator we saw is that yellow area. That's the probability of A intersect B. And that's going to be our next formula. Right. If A and B are events in an experiment, probability of A is not zero, then the conditional probability that event B will occur given that A has already occurred, and that's denoted this probability of B given A. The probability B occurs given A occurred. And here's our formula for that, like we just saw. That's the new sample space is, we know A happened, so now it's the probability of A is our denominator, and the intersection is our numerator. The probability of the intersection is our numerator. Now, in a uniform sample space, like we've been seeing, is just like with our union rule, right? We could just look at the size of sets instead of looking at the probabilities of each one, as long as we're in a uniform sample space. Remember, uniform sample spaces equal likely events. That's how we did the dice problems. That's how we did the heads and tails, right? We looked at the sequence of them, so they're all equally likely. All right, so, and this is nothing more than how we did it with the union rule. We could, in equally likely, we can move from probabilities to the number of items in the set, because they both have the same sample space and they cancel out. All right, and that's just stating the same thing that we just saw above, that we could count the probability using the size of the sets. Let's suppose a pair of fair dice is rolled. What is the probability that the sum of the two numbers rolled is a 7 if it is known that one of the numbers rolled is a 4? Okay, so let's think about that. Let's call A equal 1 is a 4. And remember what that means, at least one, right? Either one. So double counts there. And then B is the sum is 7 when I roll these two dice. And I'm looking for the probability of B given A. And we saw, because the dice problem is a uniform sample space, we could say this is the size of A intersect B over the size of A. Okay. Now, how many ways can we get a 4? You know, I'd pause it, look at your chart, get some practice. The probability is 11 out of 36, or it happens 11 times. So that's our denominator. Numerator, the size of A intersect B. Well, what can you get? A 4 or 3, or a 3 and then a 4. So there's 2. And our probability of... So the probability that we get a sum of 7, if we know that one of the numbers is a 4, is going to be 2 11ths. Consider the experiment where a fair die was rolled. Let A be the event that an odd number was rolled. Let B be the event that the number 5 was rolled. Find the probability of B given A. Again, take a minute. Maybe hit pause. Think about it. 1/3. Why? Because now we know that, what do we know? An odd number was rolled. That means that the new denominator is 3. And there's only one way to get a 5 there. Okay? That's that one. Okay. Now, sometimes we know the probability of B given A and the probability of A. This would be like the cards example we looked at before we defined conditional probability. But you'd rather know the intersection, and this is exactly like the cards problem, right? So let's say A is the event, we get king as a first card, and B is event, we get a king as the second card. Okay? Using our formula, we know, this was our formula, if we multiply both sides by the probability of A, we get the probability probability of A intersect B equals the probability of A times the probability of B given A. Okay. All right, so this is saying now what's the intersection? Think about that in words. That's saying that's the event we get two kings when we draw two cards out. All right? The first card is a king and the second card is a king. All right, and we got that intersection. And generally relate with intersections, we generally relate multiplication, which we're seeing here. And we know the probability of getting a king first, probability of A, is 4 out of 52. And now the probability of getting a king second, given that we got a king first, that's going to be 3 out of 51. And that gives me, let's see, 4 times 3. 0.0045-ish. And that's called the product rule. And that's how we use that. And here it is in all its glory. Okay. Two cards drawn from a well-shuffled deck of play. What is the probability the first card drawn is an ace and the second card drawn is a face card? Okay, so let's think about this. We're going to define our sets. A, I like blue better. A equals ace drawn first, and we'll say that F equals face drawn second. Now, we know from our formula, if we want to find, where they're being asked to find the probability of A intersect F. Okay. Now, we just learned our formula. That's going to be the probability of A times the probability of F given A. Like that. All right? That's our formula for that. And we could find these things, but I'm going to draw what's called a tree diagram here, because I think this is the best way to wrap your mind around a lot of conditional probability problems. So let's think about how we could draw this. It's going to be much like how we found the sample space for heads and tails. Okay. We have what? We could either get an ace first, or we don't get an ace first. And we know what's the probability of getting an ace? Is going to be 4 out of 52, which means the probability of not getting an ace is 48 out of 52. All right. Now, we could, not B, we used F, sorry. So now, over here, well, if we drew an ace first, then we could either get a face card or not face card. If we did not draw a ace first, we could either get a face card or not a face card. I'm going to use some different color here so we can see it well. So what I'm saying here, this edge, right, this edge right here, star, I want to fill in with, I'm thinking I already picked an ace card. Now what's the probability of getting an F? In other words, that's the probability of F given A, where this green thing is, and that's going to be, well, we have 51 cards left, and there are how many face cards left? There's still 12. Okay, so remember, this is the probability of F given A right there. All right? And we're interested in we're interested in the intersection, right? We're trying to find this intersection. We have the formula, so we know how to find it, but visually, let me show us what we're doing here is, well, we know we got an ace first, so I think of walking along that edge to get to that A, and then a face card second, so that path. And generally, over at the end of each path, that's where I think of my intersection. F intersect A, and that's equal to 4 out of 52 times 12 over 51. And it's just, and notice that it's of course the same thing as our formula, but we could visualize it. So here, so now by this one, I would think of this as probability of F complement intersect A, and that's going to be, well, I'll let you guys fill that in. But notice this is probability of F given A. That means this right here, this edge should be the probability of F complement given A. And I'm going to stop the video there, and I'd like you to fill in that whole chart. And what I want you to find is the probability of not a face card and an ace, as well as find the probability of not getting an ace and not getting a face card. Okay. Please let me know if you have any questions, and we'll see each other in the next video. Have a great day.